You know that feeling when you're streaming a movie, downloading a huge file, and scrolling through social media all at the same time? It really does feel like magic. But it's not. It's actually a whole army of invisible workers buzzing around inside your device. And today, we're going to meet them.
I mean, really think about it. It all feels so seamless, right? But behind the scenes, it's this incredibly well-coordinated effort. It's not just one single program doing everything. So the big question is, how on earth does your computer juggle all of this at once without dropping a single ball?
Well, the secret is what we can call the multitasking illusion. Your app isn't one single thing doing a ton of jobs. It's a whole team of digital workers. So let's get introduced to the two most important players on this team.
Okay, first up, you've got the process. Just think of that as the entire project, like your web browser as a whole. But inside that project, that's where you find the threads. These are the individual workers, and each one is handling a very specific task. So one thread is playing the video, another one is handling your mouse clicks. You get the idea.
And this visual really says it all, doesn't it? A single-threaded process is like one person trying to do everything in order. It's slow, it's clunky, but a multi-threaded process, that's a team. By splitting up the work, the whole app feels incredibly fast and responsive. This, right here, is the secret to how you can stream, download, and scroll all at once.
So what's a day in the life of one of these digital workers actually like? Well, a thread doesn't just pop into existence out of nowhere. It actually goes through a very specific life cycle, with different stages from the moment it's created to the moment its job is done.
And here it is. This is the entire roadmap for a thread's life. It gets created, it waits for its turn, it runs, sometimes it gets paused for a bit, and then, eventually, its job is finished. Let's break down the most important states. So as soon as a thread is created, it enters the runnable state. Now, it's not actually working yet. It's more like a worker who's clocked in and is just waiting in line for the manager, which is the processor, to say, okay, you're up, get on the assembly line. And once the processor gives that green light, the thread moves into the running state. This is prime time. The thread is actively doing its thing. It's executing its code, it's playing that video frame, downloading that little packet of data. It's on the assembly line, getting the job done.
But what happens if a thread needs something it doesn't have? Like, say, a file that's still being downloaded by a different thread? Well, it enters the blocked state. It's basically put on pause. You can think of it as taking a coffee break until that resource becomes available. This is smart because it steps out of the runnable line so other workers who are ready to go can take their turn.
Okay, so we've got this awesome team of workers, but having a team brings up a whole new problem. How do you get them to share tools and resources without causing complete and utter chaos? Well, you need rules.
And the most important rule is called synchronization. This is basically the traffic cop for your threads. It makes sure that when a bunch of threads all need to use the same thing, like, say, writing to the same file, only one can use it at a time. This is absolutely crucial for preventing them from tripping over each other and scrambling your data.
But sometimes, even with rules, things can go horribly wrong. And that brings us to a classic, nasty problem in computer science called deadlock. It's a digital standoff, and it can grind an entire application to a screeching halt. So let's just walk through how this happens. Imagine we have two workers, thread X and thread Y, and we've got two tools they both need to use. We'll call them resource A and resource B. Right now, everything's cool. They're both just ready to get to work.
But here's where the disaster strikes. Thread X swoops in, grabs resource A, and locks it. At the exact same time, thread Y goes and grabs resource B and locks it. Now look at the mess. Thread X needs B, but Y has it, and thread Y needs A, but X has it. Neither one is going to let go. They are permanently, totally stuck. That's a deadlock.
A deadlock is this fatal embrace. It's the perfect analogy. Two people meeting on a super narrow bridge, and both of them are stubbornly refusing to back up. That's exactly what's happening here. In the digital world, this just means both threads will wait forever, and your program just freezes.
So, we've got all these little workers toiling away in the background. But how does all their hard work actually connect to the buttons we click and the interfaces we see on screen? Let's bridge that gap.
Every single time you click your mouse or type on your keyboard, you're actually sending a signal. These signals are called events, and your applications have this really clever system built just to listen for them and then respond instantly.
It's called the event delegation model, and it's a really simple three-step dance. First, a source, let's say a button you click, generates an event. You can think of this like it's sending out a message. Second, that event message gets sent out. And third, a dedicated listener is waiting to catch that specific message, and it knows exactly what code to run in response. Click, message sent, listener catches, action happens. Simple as that.
So what is an event, really? It's just a notification that something happened. A button getting pressed creates something called an action event. Your mouse moving across the screen creates a mouse event, and every single key you type generates a key event. Each of these different events triggers a specific listener, which is why your application feels so incredibly responsive to your every move.
So we've got the workers in the background, and we've got the listeners waiting for your actions. But what about the actual interface itself? You know, the windows, the buttons, the text fields? Turns out they're all built from a standard set of digital building blocks.
This hierarchy diagram shows exactly how it's all put together. You start with a basic container, like a window frame. Then you just start placing smaller components inside it, things like buttons, labels, and checkboxes. It's really just like building with digital Legos to create any interface you can possibly imagine. And of course, to make sure all those digital Legos don't just end up in one big messy pile, programmers use something called layout managers. These are basically the blueprints that tell the application how to arrange everything neatly inside the window, whether it should stack them in a grid, or let them flow like text, or pin them to the edges.
So, the next time your app seems to be doing 5 things at once, you'll know it's not magic at all. It's a whole army of tiny workers, a system of listeners, and a collection of building blocks, all working in perfect harmony. So the real question is, when you see an app freeze up now, are you going to wonder if 2 of its little workers are stuck facing off on a narrow bridge?